Daniel is from South Africa. Daniel is from South Africa. Got his undergraduate at the University of Cape Town, and then went to the University of Georgia for his PhD. Did a postdoc at UCLA with Stan Osher. That's correct, right, Daniel? And is
Correct.
now a assistant professor at the Colorado School of Mines. So he works on derivative-free optimization, theory of deep learning, and optimization in general. So with that, I'll hand it over to you, and thank you very much, Daniel.
Yeah, thanks, Christian, for the introduction. Thanks to the organizers for the invitation. Yeah, so I'm going to give a talk which surveys some work I did mostly as a postdoc at UCLA, but recent developments in machine learning have got me interested in this again, and so hopefully towards the end I can tell you what those are. So yeah, the topic, it's kind of on the intersection of two of my research interests. It will draw upon tools from signal processing for problems in optimization with sort of applications to machine learning. So yeah, first off, I would like to thank all the great collaborators I've had the pleasure of working with on this project. Most of them will feature at some stage or other in this talk. Yeah, so let's get started. So the underlying sort of mathematical problem here is to minimize some scalar, some real value function f of x, possibly over a subset of RT. And we're not sticklers here. Approximate minimizers are okay, and usually f is non-convex, so in that case we're happy to settle for a local minimizer. So what makes optimization challenging is, for the most part, you don't have global access to the function, right? It's not a polynomial or something easy like that. So typically it's useful to think of optimization problems sort of mediated by an oracle, and the oracle takes some point x in the domain and returns to you a bit of local information about the function. So second order oracle returns the function value, the gradient, and the Hessian. First order, just the function and the Hessian, and zeroth order, just the function value. And so derivative-free optimization uses a zeroth order oracle, or perhaps something even more primitive. And yeah, so often DFO is synonymous with zeroth order information, but I particularly want to use the word derivative-free because later we'll see some situations where something different to the zeroth order oracle is what makes more sense. And the guiding sort of algorithmic principle here is that the oracle calls are expensive. And so you want to design algorithms that make as few oracle calls as possible, which is similar to, but not the same as, algorithms which converge in few iterations, right? And so there's some interesting trade-offs that result.
I have a question.
Yeah.
Yeah. So for this one, you start from zero order, first order, second order. So why not third order?
Yeah. There's
higher order.
Yeah. So like Nesterov and his group at UC Louvain, they have done some interesting work on third order, fourth order. They call these tensor methods.
Okay.
Yeah, you can.
So what's the benefit of considering higher orders here?
What's the benefit? Well, I guess from my perspective, it's usually dictated by the problem, right? So in some settings, you computing a gradient is impossible or completely intractable, right?
Mm-hmm.
In which case you should use a zeroth order. In other settings, like say deep learning, computing the Hessian is intractable, right? I think everyone would agree with that. And so you're constrained to use first order. So the general principle would be use as high order as you can constrained only by the complexity of computing those higher derivatives.
I see. Okay, thank you.
Yeah, thanks for the question. Yeah. So what can we say a priori about this is particularly like zeroth order methods. So let's start off with a theorem. It's by kind of an all-star cast of optimizers, and they consider a noisy zeroth order oracle, right? Their setting is maybe a little bit different, but the differences don't concern us. And anyhow, they prove a lower bound, which applies to any algorithm you could conceive of. And the point is, it depends linearly on the dimension of the problem, capital D. And so it's kind of common wisdom that the same applies even without the oracle noise. But in preparing for this talk, I couldn't find like a concise reference for this. And so I'm just pointing out that all known algorithms in this class require at least order D queries. But I don't have a crisp statement of this fact. But I know it's true. Okay, yeah, so DFO algorithms in general and zeroth order ones in particular have historically been motivated by simulation-based optimization. So that means that you have some experiment, some chemical experiment or some physical experiment, right? And that experiment depends on some parameters. Like a paper I've seen on this is trying to like optimize certain quantities, properties of ceramics, right? And so say you want to optimize the, I don't know, shininess of a new ceramic blend, right? So you can mix a bunch of chemicals together. I apologize to any chemists or material scientists because I really don't understand the specifics of this, but what I imagine is, there's a question I'll return to in a second. You can mix various chemicals, you can bake it at various temperatures, you get a compound, and then you measure its shininess, okay? And then you might ask, okay, how can I adjust the recipe to increase this quantity, right? And so that's the information that you have. And I think it's pretty clear from the situation that computing the gradient of the shininess of the compound with respect to the quantity of, I don't know, titanium is a fool's errand, right? It can't be done, okay? So that's a setting where for which a lot of zeroth order algorithms have been developed. Currently, the source of applications is mostly from machine learning, at least, and that's my perspective. And so we'll touch on the first application in a little while. The second will come up towards the very end of the talk, and the third one is what I'm currently interested in, which perhaps we can, I don't know, discuss offline or something. But the problem is, what's common to these three applications is the dimensionality is much, much larger than previous guiding applications. Right? So 10 to the 5 variables, or sometimes much higher, right? And so the goal here is to design DFO algorithms that depend sublinearly on the ambient dimension. And this is probably a good time to flip back to the slide and address the question. F is assumed known. So I'd have to check Yanis. I think this is a stochastic optimization setting. So you have access to you can sample it, but I guess the true objective is not explicitly accessible. I hope that answers your question. Anyway, so now that we have this in front of us, right? Again, I should emphasize that this is a universal bound, right? So for generic functions that are strongly convex and Lipschitz and all those nice things, you can't do better than linear in D, right? And so to achieve this goal, we have to somehow focus on a special class, and we'll focus on functions with sparse gradients. Okay. So a definition, we say that a vector is sparse if most of its entries are 0. and this is usually quantified using this zero pseudonorm, right? Which counts the number of non-zero entries in a given vector. And there's several ways to make this, or to define a notion of approximate sparsity. I'll focus on compressibility here. And so, what this will mean for us is that if you reorder the entries of V from largest to smallest in magnitude, then they decay rapidly, right? And you can quantify this in various ways, but I'll say they decay like 1 over k. Okay. Yeah. So it's a observable.
So this pi here is this reordering, like from largest to smallest.
Yeah, pi is just a permutation that reorders from largest to smallest. Yeah, thanks.
Is there a definition for incompressible?
I would say that if all the entries are roughly the same magnitude, right?
I see. Yeah, because it just reminds me of the compressible, incompressible in fluid. So, but that's but that's
analogy. I don't know
a little bit different.
if we connect that. I think here is like compressible in terms of like information theory, right?
Yeah.
And so here it means that if there's you can do a lossy compression, which captures most of the information.
I see. Thank you.
Yeah. So it's sort of an observable phenomenon that I've observed and others have too, that often high-dimensional objective functions have sparse or compressible gradients. And so heuristically, this can arise because of one of two sources. The first one is simply that they're over-parameterized. When practitioners are designing objective functions, it makes sense, and it's probably the right thing to do to throw in every variable that you think might affect the outcome, right? But in practice, some of them are probably extraneous. They don't really affect the objective value, right? And so in that case, the gradient of f will be 0 in these directions. And second, and kind of more interesting, effect of a view, that's a typo, I meant to say effect of a few xi. So even with functions where every coordinate is important somewhere, they're often at any given point, only a few coordinate directions dominate. They affect, f is very sensitive in a few directions and insensitive in all the other directions. So that results in a compressible gradient. Okay. And so to convince you of this, oh, that's even worse than I thought it was. My goodness. So here are some examples of compressible gradients in the wild. Beamer has inexplicably formatted this picture with a black background. Who knows why that happened, but life's too short to worry about such things. Anyway, so let me walk you through them from left to right. So this is the objective function of an adversarial attack on a neural network, and I'll define the actual function here in a few slides. But the trend is clear, right? Which is that if you order the gradient components from largest to smallest, then they drop off rapidly, right? And so we didn't do anything too fancy here. We took randomly selected points of this objective function, and we did 100 randomly selected x, and so that's why there's some shading here. And so these pictures show the same thing, although it's hard to make out as they're formatted. And there are many typos here too. This is what happens when you prepare your slides the morning of. But the trend is clear, right? And I want to highlight that these two problems are not fancy. They're from a standard benchmarking suite and optimization, MGH. They're not designed to exhibit compressibility. right? But it's very interesting to note that they do. Okay. So I want to develop an algorithm that will, an optimization scheme for functions which have sparse or compressible gradients. And to start off, I want to view the problem of approximating a gradient from a signal processing viewpoint. And we'll frame it as an inverse problem. And so to start, we'll do this sort of finite differencing in a fixed direction Zi. This is a very standard operation in zeroth order optimization. And ignoring like higher order terms, this is approximately equal to the inner product of the direction and the true gradient, right? And so if you do this m times and you form a vector y, then y is approximately equal to the matrix Z times the gradient, where Z has Z1 through Zm as its rows. Okay, and so this is like a linear inverse problem, right? And of course, you can't for generic signal, in this case generic gradient, you couldn't solve this with fewer than capital D measurements, right? But if you have a structural prior, like you know that the gradient is sparse or compressible, then there are things you can do, right? And so we'll draw from the theory of compressed sensing. And so in theory and in practice, if the gradient is S sparse, then you can recover a good approximation using only S log D measurements. Okay. So I'm saying measurements here, and I've also sort of dropped the oracle notation bit, but keep in mind that each measurement here will take one we'll make one query to the oracle, right? So we're only making this many function evaluations, oracle queries in the language of a few slides ago. Yeah, so this works equally well for compressible gradients. Theory extends nicely. And so what my collaborators and I proposed to do was use the COSAMP algorithm, which was developed by Joel Trapp and Deanna Needell, who's now at UCLA. But I'll note that there was another group at Carnegie Mellon that came up with a very similar idea a little bit earlier than us, but they used lasso instead of COSAMP, and there's some differences to how zeros. Okay. So with that in mind, this is the Zorro algorithm. So it stands for zeroth order regularized optimization. I won't say much about the R, the regularization here, but I think the idea is pretty simple, right? So at its core, it's like a gradient descent, but with an approximated gradient. And the only like smart thing here we do is approximate the gradient by making so m of these finite differences in random directions. The randomness is important for the compressed sensing theory, and then solving this problem over here using the COSAMP algorithm, which I haven't said too much about. Okay. And so here's a sketch of our main result. It's simplified and some of the detail is hidden. But if you assume these sort of standard optimization conditions, and then this non-standard one, but which I sort of motivated from experimental observations, then the Zorro algorithm is sublinear in the dimension, right? And it's in fact logarithmic in the direction. So that's quite nice. The paper has many extensions. Again, the R and the name of the algorithm is for coping with regularizers, but I won't say anything about that here. Okay, so two-step outline of the proof. So kind of carefully sifting through the compressed sensing theory, you can arrive at this error bound. So this term here is just from compressed sensing. And then this term, the error due to smoothness, it sort of comes from the Taylor expansion of F, right? So it depends on Lipschitz constant and then also the Hessian term, right? But you can quantify this exactly. And then there's a lot of work on so-called inexact gradient descent. So this is adjacent to, but not the same as stochastic gradient descent. But yeah, this is gradient descent with an approximation to the gradient, not the true gradient itself. And there's a lot of work there, but we couldn't find the exact results we needed, so we filled in a few gaps in that literature, and that's kind of how that went. Okay, so now I'd like to get to kind of the first application. So this is for classifiers. So for us, a network, a neural network will usually be indicated like this, right? The subscript theta denotes the tunable weights. We assume that the network is pre-trained, so those weights are fixed. And then R capital D is, we can think of as an image space, right? So maybe D is, I don't know, 1,000 by 1,000. What is that? A million? Yeah. Okay. And then the output space is essentially a probability score for each class in the problem, right? And then how you actually do classification is you find the argmax, right? You find the class or category with the highest probability. Okay, so dating back 10 years now, it's been observed that neural networks lack robustness for classification, and usually the deeper the network, the less robust it is. And so for us, what that means is that for a natural data x0, so like a true image, you can add very small perturbations to it that will change the classifier's classification, change the network's classification. And Carlini and Wagner wrote a nice paper that formalized this as an optimization problem. Okay. And so to be clear, the problem of finding a adversarial attack, right? Defending against them is much harder and a topic for a different talk. But so if you want to find such a perturbation, right, it's quite natural. What you do is you find X maximizing the yeah. So this quantity here in the inner thing here is the gap between the perturbed image, the probability on the true category, and the next one, right? And so and then the second max is, I guess, a little bit extraneous, right? Just to make it non-negative. It's not so important, right? So minimizing this loss, we'll find an X where the probability on some other category is larger than the probability on the true category, right? You drive this loss to 0, and it means you forced a misclassification, right? Okay, and so this is a derivative-free problem because in realistic threat scenarios, the adversary doesn't have access to the weights theta, so they only have say API access to n of theta, right? And so you can't do backpropagation, you can't compute the gradients exactly, right? All you have is function evaluations, so zero-fold oracle. Okay, and so so we did generated some adversarial attacks using Zorro. And the first point I want to emphasize is that if you start from x equals 0, so that should be x equals 0, then at each step of Zorro, the gradient is S sparse. So you only make S entries in your perturbation non-zero, right? So after k iterations, there are at most k times s non-zero entries. And the second thing that I want to show you is that, so if we go back to this picture, this is what I'm showing you over here. This is the gradient of that Carlini-Wagner loss function, right? For a realistic setting, it's inception V3, it's not a vision transformer, so it's no longer state of the art, but it's a pretty decent convolutional neural net for ImageNet problems. Yeah, empirically the gradient is very sparse. And so the sparse approximations make sense. And if you run Zara for just a few iterations, you only change a few of the pixels, right? And this is kind of what you're seeing over here. So perhaps this doesn't come out too good on your screens. You can see this this kind of speckle noise, right? And so the clean picture, I think, is pretty clear what it would be. It's just the picture without the speckle. And then we run Zara for a few iterations, and it finds this very interesting speckle pattern. It's different for every image, and it forces a misclassification, right? And so, yeah, we think this is kind of interesting. There's a lot of other work on doing low L2 norm adversarial perturbations, right? And those are typically kind of imperceptible to the human eye, right? And these are like low L0 norm perturbations, right? Which are more visible to the human eye because they have more energy at each changed pixel. But it's interesting to know that it works. Cool. Yeah. Maybe this is a good time to pause and say, do you all have any questions before we continue?
So could your algorithm find other types of perturbations? You said this is, zero norm perturbation. Can it find two norm, infinity norm, one norm perturbations bounded by a certain amount that would still give misclassifications?
Maybe, but probably not. So often when people do this tax, they explicitly enforce say the two norm constraint, right?
Mm-hmm.
And you can use like projected gradient descent or whatever. And so when we did this attack, we didn't explicitly enforce any constraints. We just used the fact that Zara only changes a few pixels at every step, so it's naturally results in a sparse perturbation, right? So to answer your question, you could try and use Zara for like a low L2 norm perturbation by just enforcing this constraint. But I don't think that would be an optimal use. There'd be other approaches which are better for that. Yeah. Thanks for the question. We'll see something kind of intermediate in a few slides. Yeah, so this works for a problem size around 10 to the 5. That's roughly the size of the input images once you vectorize. For D much larger, you run into some problems. The first is just that the ZI, so the random perturbation directions that we used in, let's just go back to Zara, like over here. They need to be either like Gaussian random vectors or Rademacher random vectors, both of which are dense, right? And so when when they need to be million dimensional, then generating and storing these random perturbations can be tricky. And then the second issue is that so generating this gradient approximation using cosam, is it worth going back? Sure, why not? So solving this problem is computationally quite taxing in capital D, right? And so, for derivative-free optimization, this is sort of a secondary problem because we care much more about the number of queries made than the computational complexity of each iteration, right? Nonetheless, it becomes a problem just because, you know, I don't have all day, neither do you, and running cosine to generate a gradient for a single step can take hours if d is much greater than 10 to the 5. So, sorry, was that a question? So we started thinking about whether you could find something that is query efficient and also computationally efficient. And the key idea is to use coordinate descent or block coordinate descent as like the base optimization algorithm instead of the gradient descent, which is sort of the base of Zaro. And so we wrote a paper that fleshes out this idea. I just put myself here because there wasn't enough space in the footnote space, but Yu-Chen Lo was heavily involved in this. He was an undergrad at the time, and he's now a PhD student at Northwestern, and Han-Chin Tsai and Guo Taoyan were also involved. And yeah, so let me just jump to the algorithm. Yeah, before I do some notation, so this G with a hat and a superscript will denote the gradient with respect to the jth block of coordinates, right? So this might be a block of 1,000 coordinates or something like that. And so this is the algorithm that we developed. The core over here is the same as Zaro, right? You take these measurements in random directions, and then you use COSAP to reconstruct a sparse approximate, and then you take a step. We're using notation slightly here, right? This is a block gradient, and then we're taking a full step, but you can just imagine zero padding this gradient so that it becomes d-dimensional again. So fairly straightforward, except for one key step, I suppose, which is the randomization here. So it's key that you randomly assign variables to blocks. And why this is important is you need each block gradient to be approximately sparse, right? And if you didn't randomly assign, then it could be the case that like the first 100 entries are the ones that have like non-zero gradient entries, and the rest of them, you know, are zero in the gradient. But then if you choose your blocks incorrectly, you won't get a sparse block gradient. Okay. So key step here is randomization. And yeah, so we proved quite a satisfying theorem about this. The setting is a little more restrictive than Zaro. We assume exact sparsity of the gradient for simplicity, which is not a realistic assumption, but you know, it's pretty close to being realistic. We choose so J blocks. So this is a little typo, that should be a capital D. And J should be much greater than the gradient sparsity, but much less than the dimension of the problem. And so we're able to quantify the number of queries. I'm using a tilde on my big O to suppress logarithmic factors. But this is the same up to an extra logarithm as the query complexity of Zaro. But the compute is greatly reduced, right? This is CD over J squared. And so one of the key steps, again, the randomization ensures that if the full gradient is approximately S sparse, then the block gradients are approximately S over the number of blocks sparse. So we prove that. And then the compressed sensing literature that I alluded to earlier guarantees that you have a pretty good approximation of the block gradient. And then we use some fairly recent results on block coordinate descent with an inexact estimate of the gradient to conclude. Yanis, I don't quite understand your question.
Yes, you mentioned that it's not sufficient to randomize, but you have to randomize in order to achieve sparsity.
Mhm.
So I was wondering how many iterations could that take, and if that can be an algorithmic an implementation bottleneck. From your experience, can you tell us that process? How is that achieved?
So let me say it back to see if I understood your question. So firstly, there are two distinct sources of randomness here. It's the random assignment of variables to blocks, and then the zi are random vectors. And so more directly, we just need to do this part once, right? You just do a single assignment of variables to blocks.
But then I'm just wondering. You said you want to achieve sparsity. Just randomizing is not enough. That's something. Maybe I didn't understand it correctly, but
Yeah. So we assume sparsity, I guess. So we assume the gradient is sparse, and just to reiterate that what we want to avoid is, okay, it could be sparse, but the first 1,000 of vectors could all be the first 1,000 entries of the gradient could be the non-zeros, right? In which case, if you naively choose your blocks, you hit a problem.
okay, so that's the algorithmic check. So that's kind of like finite step. It's not something that can be like non-converging, or you have to spend like
Yeah. So it's like shuffling
okay.
a deck of cards, right? So imagine I hand you a deck of cards and the 4 aces are on the top, right? That's the bad situation we want to avoid, right? But you shuffle that deck once, and with very high probability, the aces are pretty much uniformly distributed throughout the deck, right? So that's fine.
So could that be a problem as you go to bigger and bigger sizes?
Not really, because randomly permuting is a pretty cheap operation. Yeah. So we don't observe that being an issue. And again, it's a once-off cost. So it's not so bad. Yeah.
Thank you.
That's the question. Yeah. Okay. So where are these large problems, right? What natural zeroth order problems have dimension higher than 10 to the 5, right? Not necessarily image attacks, because as I showed you, even ImageNet, the size of the input, the image size is relatively small, right? So we look at the problem of audio classification, right? And so this is a kind of a sub-problem called keyword classification. And so think of like your Alexa speaker or Siri. I feel like none of these do a good job at this problem, but this is what they're intended to solve, right? They're supposed to hear and classify a small number of keywords or wake words, as they're sometimes called, right? And so these slides were made, we started this problem in 2020, right? And at that time, convolutional neural networks were state of the art for audio classification problems. So this is just kind of a sketch of how it works, but your audio is a 1D signal, right? And then they do a transform. Here it's called like the Mel frequency transform, right? So it's kind of like a time frequency space. That's where you're transforming to. So you generate a 2D signal. And the MFT Mel frequency transform is designed to sort of mimic human hearing, right? So let me not say much more about that because I'm not an audio engineer. Anyway, so yeah, and so then now you have like a 2D signal, an image, if you will, and so then you use a convolutional neural net to perform classification, right? So this is no longer state of the art. Transformers do much better at this now, right? So if anyone's interested, these experiments, could be redone. Anyhow, so while many other works in derivative-free optimization seek to reduce the dimension of the problem, given that we have this ZOBCD algorithm, this block coordinate descent, we can no longer be afraid of high-dimensional problems. So we actually increase the dimension of this problem, and we do so using sort of pre-processing with a continuous wavelet transform, right? And so we use a Morse wavelet, and so this results in something which I guess is not too dissimilar to this, right? You have like a mother wavelet, and you can fix a bandwidth, I suppose, of this wavelet, and then you shift it along the input signal, and you compute the convolution, I suppose, the product of the wavelet and the signal, and that gives you coefficients, and then you can shrink the wavelet and do the same thing, right? And so the more times you shrink the wavelet, the higher dimensional the set of all these wavelet coefficients is, right? But you can extract more sort of fine-grained information from the audio signal. So what we want to do is do a adversarial attack, right, on speech signals, so audio signals, and we want to craft this attack in the wavelet domain, right? So here is the wavelet transform. I'm abusing notation by writing F inverse. It's not it's not a it's not a surjective function, right? So it doesn't strictly have an inverse, but it's the inverse wavelet transform. And the loss function is the same. It's this guy, right? But again, it's just like I'm optimizing in the domain of wavelet coefficients and then transforming back to the time domain and adding that to my base signal. And the hope here is that you have a lot more space to move, right? You have a lot more things you can change, as opposed to just generating your attack in the time domain. And so our hypothesis was that this would result in better attacks, and it does. And so, as I mentioned, this is an over-complete transform. So the resulting dimension, the dimension of the space of wavelet coefficients was 1.7 million. So this is the largest DFO problem I'm aware of that has ever been attempted. Yeah, so it works well. Here's just kind of a snapshot. We do a targeted attack, which is a little more complicated than what I sketched earlier. It's that we don't just want to force a misclassification. We want this audio classifier to classify a clip of saying, I don't know, no, as someone saying left, right? And so that's why you have this matrix of values, right? So kind of interesting, some clips are easier to attack to others. I should add that, so this is on the speech commands data set, and it's 10,000 clips, each is about 1 second, of various people saying these words, sometimes with background noise. Okay, and so, and then on the right, I show you the average distortion of the attack that we found, right? Measured in decibels. Okay, so this is, state of the art, but, with some caveats, I suppose. Firstly, maybe most importantly, this was state of the art in 2021, right, where we wrote this paper. So maybe things have changed. And then secondly, you have to be a little bit judicious with your comparisons. So a lot of work in this area uses a white box model. So that means they have full access to the weights of the victim model. And that obviously makes the problem a lot easier, right? And so that's why they're able to generate very low energy distortions that force misclassifications, right? So those are higher energy, but importantly, we do use a black box model. And this is by far the highest attack success rate of any black box audio attack that I'm aware of. I actually have some audio clips of the attacks. They're kind of interesting. So if we have time, I'll play them to you. That's what this is meant to be. Okay, so we can come back to the audio visual part of the talk later if we have time. But I'd like to move to the third topic, And so, I mentioned that I'm using derivative free over 0th order because I want to specifically allow for oracle modes which are below 1st order, right? So you don't have any gradient information, but are not the 0th order oracle. And so an instance where this arises is when the objective function is something intrinsic to or internal to a human. So a good example of this is getting a new pair of glasses, right? Going to the optometrist, right? So someone internal to you as the patient is the optimal prescription, right? But the optometrist doesn't ask you what is your optimal prescription. You don't tell them negative 3.5. Instead, they offer you paired comparisons, right? So they'll offer you 2 prescriptions and they'll ask which is better, A or B, right? And they use this process to improve the fit of the prescription to you as the individual. And so this setting is of perennial interest in machine learning, and it's variously called human-in-the-loop learning, preference-based learning, or comparison-based learning. And so building on that optometrist example, we can reliably gain information on this human internal objective function via paired comparisons. And so that's exactly what the optometrist does, right? So you offer 2 examples to a subject, and they tell you which one is better, right? And because we're doing minimization, better means lower objective score, right? And this is a single bit of information. It's just the sign of the difference between Fy and Fx, okay? And just for completeness, I want to list what a noisy comparison oracle looks like. And this is the same thing, but now there's only a probability that the oracle gives you the correct sign, right? And then with probability 1 minus p, it gives you the incorrect sign, which is -1 times the sign of Fy minus Fx, okay? And so we'll combine, I guess, this with earlier tools. I want to exploit gradient sparsity to design comparison-based algorithms, which are sublinear in the ambient dimension. And the key tool is, again, a signal processing field. It's 1-bit compressed sensing. Yeah. So, okay. Yeah, we have a bit of time. So briefly, what is 1-bit compressed sensing? So I guess kind of historically, when people started exploring this notion of compressed sensing in the mid-2000s, this question came up of, this works in theory, right? If you have infinite precision measurements and infinite precision knowledge of the perturbation Zi, but that's not true in practice, right? So if everything is quantized, do things still work? And Buffonis and Baroniuk, I think, I don't know what motivated them to take this to the logical extreme, but they did. And they said, okay, well, what if you just have 1 bit of information on each measurement, right? And so if you, imagine this product over here encoded in like 32-bit floating point format or whatever, right? The first bit is just the sign, right? So they said, okay, just retain that information. And what's really cool, so earlier we saw the COSAMP algorithm for recovering a signal from sublinear number of measurements of this form, like full linear measurements. But you can recover using just these signs, right? And so the surrogate optimization problem, the thing you want to solve, is a little bit different, and it turns out to be just a linear program, right? And so again, these are signs, right? And so you want to maximize the sum. So you want to find a V such that the inner product with all of the measurement vectors Zi aligns with Yi, right? This is actually a max problem. Let me point that out. Of course, you can turn it into a min pretty easily, but yeah. So Yaniv Plan and Roman Vershinin, there are other works in this area, but I think their paper is quite nice. They show that this scheme works, right? And there's an important caveat, which is that the magnitude information is completely lost of V star through this quantization process. So there's no hope of recovering it. So you measure error with respect to the normalization of the target vector V star. Okay, so here's a slide offering some intuition as to why this might work. In the interest of time, I'll skip and I'll jump to the optimization scheme. So yeah, so what is the core line here? The core is that we can only access F via this potentially noisy comparison oracle, right? If you pass as input some fixed point X and then a small perturbation of that, right? What the comparison oracle is doing is returning the sign of f of x plus delta zi minus fx, and you do a Taylor expansion, you ignore second order terms and higher, and what you're getting is the sign of the inner product of the gradient and this random measurement direction, right? So this connects to one-bit compressed sensing. We made this connection, yeah. So our algorithm SCOBO, the core of it is the novel part, I suppose, is the gradient approximation. We do this using tools from signal processing. Specifically, we do this by solving the one-bit compressed sensing problem. Here it is. Okay, and then take a step of gradient descent with this approximated gradient and continue. So we proved that it works. This was hard. So again, here's a simplified version of the main result. This paper appeared in Applied in Computational Harmonic Analysis last year after a lengthy revision. We focus on strongly convex functions. So technically restricted strongly convex. This is a technical assumption. I didn't specify it here. I apologize. We also assume that F has S sparse gradients, right? That's the, I haven't written it out, but yeah, S sparse. And then you have to choose your step size carefully, right? You have to choose your step size to be proportional to the square root of your target accuracy, right? That's kind of the hard part. And then the rate you get out is it's not great, right? So it is sublinear in the the ambient dimension, right? It depends on S, not capital D. But the dependence on the target accuracy is worse than you would expect for a strongly convex function, right? So if you have access to first order information in a noise-free case, then it's log epsilon here, and in the stochastic case, it's epsilon or epsilon to the half, I forget, right? But you would expect this to be epsilon to the -1 or less, right? But yeah, I mean, I think not to put my own work down, the amazing thing is that it works, right? And it works pretty well. And importantly, you have sublinear dependence on the dimension. So this opens up a whole new set of applications for comparison-based optimization. Here's a 2-point summary of the proof. I won't say much more about that, and I'll just jump to some pictures. And so, yeah, as I mentioned, it works really well when the gradient is sparse. So here are 2 test functions that we cooked up. The first one we called this the sparse quadratic, right? So this is just a simple, well-conditioned quadratic function, but it only depends on the first 20 entries. And so here are the results for that. We're comparing SCOBO against some other competitors, which I'm happy to elaborate on after the talk. And there's not so clear a difference. But if you study a hard problem like this max k squared problem, right? So the difference between this one and this one is that the subset of components which are active, which contribute to the gradient, changes at every point, right? So this is a hard problem, but the gradient is sparse at every point, and our algorithm just does much better. And then finally, just a shout out to my student Isha Snevin, who was an undergrad at UCLA and is now a master's at NYU. And she did a very thorough sort of exploration of how these algorithms perform on problems which are not necessarily sparse, right? So this is a performance profile for the Q-test dataset, which is, again, a common optimization benchmarking suite. None of the problems are a priori sparse. And I won't say too much about performance profiles, but higher is better, right? And the quicker you get higher, the more problems you solve using few queries. And so Scobo does the kind of the worst here. Algorithms which are kind of it's just kind of overkill in this setting, I suppose. But the point is, it does solve these problems, right? And again, these are not exhibiting sparse gradients, right? So it works out of its assumptions. Yeah, so a lot more I could say. I wanted to just take another minute or two to sort of speculate and tell you about some current and future work. And this will sort of answer the why we care about comparison-based optimization. So in, for example, reinforcement learning, you train an algorithm that's designed to maximize a scalar reward function, right? And so this reward function is cooked up by engineers, and it's kind of hard to design a good reward function, right? That captures, all the things you want the agent to be good at in this environment. And as a result, pathologies often occur. And I have a brief, I'd like to show you a web page briefly that has a video that's pretty interesting. So this is a little bit older, perhaps you've seen it before. But this is just a blog post from OpenAI, and they study RL for games, right? And so this game is called Coast Runner, and it's basically a boat race, right? But within the race, there are these little like power-ups you can get, kind of like the coins in Super Mario, right? And so each of those has a small but non-zero reward function, contribution to the reward function, right? And so what happens? Can you see the video, by the way? Okay, yeah. So what happens if you train in the setting is the algorithm learns this behavior, which is that it completely disregards the objective of completing the race and completely disregards like any damage, and it figures out the period with which these little tokens regenerate, and it just makes a loop and it just keeps collecting these tokens, right? And hitting the walls, hitting the other ships, not finishing the race. Terrible, right? Completely unaligned with what we want this agent to do. But it's maximizing the reward, like it's doing what we told it to do. So the issue here is that there's just a lack of alignment, right? And it's kind of impossible to fix this using just better reward functions, because there are always things that won't be captured, right? And so a better thing to do is to at least partially incorporate human feedback, right? And the best way to do this, well, not the best way, but a good way to do this is to show humans pairs of rollouts. So that's the trajectory followed by the algorithm given its current parameters, and ask them to choose which is better, right? So this was explored by Paul Cristiano in 2017. It's called RLHF, right? And what's super interesting is that this is exactly what's used to fine-tune large language models. So the difference between like GPT-4 and ChatGPT is that ChatGPT has been tuned using RLHF, right? And they do comparison-based they should do comparison-based optimization here. They do something slightly different, right? But yeah, so that's something that my student Jordan Pettyjohn is currently looking into, and I think that's quite interesting. Yeah, so I'm over time, so let me stop. Thank you very much. And if you have any questions or comments, feel free to send me an email.
Thank you, Daniel. Yeah, we are over time, so if anyone needs to take off, they're welcome to, obviously. If anyone has any questions, do you have a minute to stick around?
Yeah, we're open anytime.
Does anyone have any questions? I actually wouldn't mind hearing these audio like disturbances that your algorithm produced if
Sure,
you're willing
yeah,
to
let
share.
me find them. Okay, so it's a bit like staticky. So I would advise you to hold on.
Right.
Yeah, okay. Did you hear that?
Yeah, I was here saying someone saying right.
Yeah, so it's right, and
Okay.
then there's a little bit of like crackle, and that's the perturbation.
Right.
Ah.
And that
Oh, I see. Okay.
to left.
Right.
So yeah.
So all you've added is a tiny little crackle at the end,
Yeah.
or underneath it, maybe.
Yeah. And again, it's not